So on to 1.3, exponential functions. All right, so first, exponential growth. Yes, you were. So probably would be good to kind of define an exponential function here. So we'll do that and then talk about growth and decay and then just get into some examples. All right, so let A be a positive real number other than 1. The function f of x is equal to a to the x is exponential with base a. So remember, an exponential function that's a growth function looks something like this. Okay, as long as it's not shifted, it never crosses the x-axis. And if we're dealing with exponential decay, it just goes the other direction. And then I'm just going to do a little refresher on rules of exponents. Okay, we're going to have a is greater than 0, b is greater than 0, and x and y are real numbers. So we've got a to the x times a to the y is equal to a to the x plus y. A to the x times b to the x is equal to a times b to the x. A to the x divided by a to the y is equal to a to the x minus y. A divided by b to the x is equal to a to the x over b to the x. Why did I put number 5? I skipped 4. Is that what y'all were saying? Did y'all say that? Did I skip 4?
No.
No. I don't know why. I just randomly wrote 5 after 3 and yeah, I don't know what I'm doing.
We were talking about how we're going to become seniors.
You're going to become seniors?
Yeah, and then we were like, wait a minute, we are seniors.
Oh, I was like, you are. Then the last one, a to the x raised to the y is equal to a to the y raised to the x, which is equal to a to the x times y. And just because it's going to come up a decent amount in problems, the half-life of a substance, specifically a radioactive substance, is the amount of time it takes for half of the substance to change from its original radioactive state to a non-radioactive state. Okay, and it does so by emitting energy in the form of radiation. Function y is equal to k times a to the x for k greater than 0 is exponential growth if a is greater than 1, and exponential decay if 0 is less than a less than 1. Alright, so some examples out of your book. When we go to look at some of the word problems and stuff, we'll actually, in your book, just read through some of the examples that they have and talk through them before we try one out of the homework, because a lot of times the book only does like 1 or 2 of each type, and I just don't feel like that's enough. But I feel like with their examples that they've already worked for you, they're usually pretty good. But for the first part, these just say to graph the function and state its domain and range. So again, you can graph these on your calculator. So number 2, we've got y is equal to e to the x plus 3. So you can graph that and see what that looks like. So let's see, e to the x plus 3. What?
I just hope some of the parents graduated. They're this really tall guy, and then this also really fast guy. Who's fast?
Alright, so with this graph, what happens to it?
Well, it's probably gonna shift.
It's going up 3. So, we need to find the domain and range. So what would the domain be for this function? Yep, all real numbers. How about the range?
Probably everything above 3.
Are we including 3 or not including 3?
You are
Not including 3 because there's an asymptote there. So if we just graph the parent function that's an exponential, we never cross the x-axis. So when we've shifted it up 3, we then never cross the 3. So we can get as close to it as possible, but we can't touch it.
It's so annoying.
Let's look at number 4. So we've got y is equal to -2 to the negative x minus 1. So based on what this graph looks like, what is our domain and range? All real numbers. It may not always look like it, but pretty much it will always be all real numbers. Now, if it's one of those really weird graphs that like gets reflected some way or something like that, I suppose there's a chance it wouldn't be, but for the purpose of this book, pretty much will always be all real numbers for the domain. How about the range?
Yeah, it would be like
Everything under -1. So -infinity to -1. Okay, because it's reflected over, which is why it looks like that, and then it's moved down 1. Alright, seems like we're pretty good with domain and range, so let's go to the next thing. Rewrite the exponential expression to have the indicated base. So we have something like number 6. So it says 16 to the 3x, but we want it in base 2. So I think we touched on this a little bit last year in pre-cal. Do y'all remember how to change the base, or what we need to do to change the base from 16 to 2?
Draw L or E. One of those.
We don't have to do that for this. That's for a log to an exponential, or exponential to a log. This base is changing 16 to a 2.
Oh, something about 4.
Okay, so this is going to now be 2 raised to something. It's obviously still got the 3x up here. So how do I go from 2 to 16?
3. It might be 3.
What's 2 cubed? Huh? It's 4.
Or what?
2 times 2 is 4, times 2 is 8, times 2 is 16.
4 times 2? Oh. That's 4 times 4.
Okay, so we would put this 4 up here.
Yeah. And then 2 times 8 is 16. But I was thinking like 4 times 4, and I was thinking like 4 squared.
And then we need to simplify this. So this is 2 to the 12x now. Okay, do we see where that's coming from? No? Okay. All right, let's look at number 8 to see another slightly different example. 1 over 27 raised to the x, and we want to change it to base 3. So I want to go from 1 over 27 to 3 raised to the something. I know it's going to have the x in there, obviously. So 3 raised to what power gives me 27? Okay, 3 to the third would give me 27. Because it was on the bottom, we need to make it negative, so it's going to be 3 to the negative 3x. All right, so the next stuff says to use a graph to find the zeros of a function. Do y'all remember how to find zeros of a function?
Kind of. We can do substitution. You can do the crossing out one. Elimination is what it's called. And then we can do the other ones. We like put it into a factor of the polynomial and set that equal to 0.
So you could tell me what the zero of this is.
Absolutely not.
Could you do it with a graph?
Maybe.
Okay, so in your calculator, okay, put in that graph just like you have been with the other ones. Also, did you get a new calculator, Melcher?
I did. I got it for the SAT. Only to not really use it on the SAT. I took my SAT in Florida.
In Florida?
In Florida. We went on vacation and my mom jumped the gun on me and was like, oh yeah, by the way.
You have a vacation, but just kidding, you have to take your SAT.
I was like, why don't we down here? We're gonna have an SAT. And I was like,
My cousin, because of everything that happened last year, she's only a junior now, but because of everything that happened last year with the hurricanes in Louisiana, they scheduled her ACT in Houston. So they drove over to Houston to stay with my cousins and my other family, and she took her ACT over there.
At least they went over there specifically for the SAT. I went over there thinking I was on vacation.
And then you're told, oh, just
And
kidding, you're
like,
taking the
I'm not
SAT.
gonna take the SAT. Now study. And I was like that's gonna happen.
It's funny.
Really study.
All right, so if you hit the second and then the trace button, okay, on your calculator, that brings up calculate and then a bunch of different options. Number 2 is the zero function. And then your calculator is going to ask you some questions. It's going to say left bound, so you're going to come to the left side of where it crosses the x-axis. And then it's going to ask for the right side, so you're going to bring it up above the x-axis to the right of where it crosses. And then it's going to want to know if you want it to guess. And so you're obviously going to hit enter. And it should give you something where x is equal to some value and y is 0. What x value did you get?
1.3, 1.4, 1.6.
Alright, so we'll call it 1.4. Just easy. Your book will round to a couple decimal places, but I don't really care. So the 0 is at 1.4. Okay. Now, obviously, that's what the question asks, so I'll know what that, you won't have to write the 0 at blah, 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 but. All right, so let's do one more of those. Number 12. So same instructions. F of x is equal to 3 minus 2 to the x. And then use that trace function or that calculate function and find your 0 of this one. And tell me what 0 we get here. 1.6. The ones that are like match the function with its graph, I don't really care that much about those. If you want to do it, that's fine, but not something I would put on a test, so there's not really a point in dealing with it. All right, so let's see. All right, so sliding over to 21 through 32, it says to use an exponential model to solve the problem. Okay. Some of these are harder than others. The growth ones are probably easier than the decay ones, in all honesty. We're going to just do like 1, maybe 2 examples. And then I have a worksheet of problems that are printed out that have solutions on them that I just feel like they do a really good job of making them really like plain and simple. So I'll probably narrow down to the fact that on the test, these will be more so what you're tested on, other than maybe like a couple of them that I give you guys to try on your own. But I'll get copies of this for tomorrow because I had forgotten that I had this worksheet to give you guys. So let's start with number 22 and just go from there. All right, so this is a population growth problem. So the population of Silver Run in the year 1890 was 6,250. Assume the population increased at a rate of 2.75% per year. It wants to know the population between 1915 and 1940. It wants to know what the population was in 1915 and in 1940. And then to approximate when the population reached 50,000. So to start with, okay, we're starting with the year, what did it say? 1890. Okay, and the population was 6,250. It says that the population increased at a rate of 2.75% per year. Okay, but obviously we don't really do a whole lot with percent, so if I need to make that a decimal, I have 0.0275. Really quick, a formula that I don't actually think your book mentions in this section, which is kind of crazy, but that you need. Guess they just expect that you remember it, is P of T is equal to P times 1 plus R raised to the T. Yeah, the other formula. Okay, just checking which formula I wanted to use. Okay, so we're gonna plug stuff in to this formula here. So P of T is equal to, so P is that initial population value. So 6250 times 1 plus, and I should have specified this is R here, this rate. So 0.0275 raised to, Okay, t is in time. Okay, so the first thing it wants to know is what the population is in 1915, and then we want to know the population in 1940. Okay, now that doesn't mean that t is 1915. Okay, t is the time since the initial in this case. Okay, so how many years passed from 1890 to 1915? 25. So we're going to raise this to the 25. And then you guys can plug this in your calculator and we'll get the population for 1915. And if it gives you a decimal, just round to the nearest whole number. Because obviously we can't have a part of a person. How many people? 12,315. All right, and then we're going to do the same thing for 1940. So we set it up the same way. The only difference is how many years passed from 1890 to 1940. 50. So you do the same formula, but raise it to the 50 instead. What'd you say?
I don't know, whatever you said.
I heard 24 something. 24265.
Just 24,360.
So technically this is part A of this problem. Okay, this was a two-part problem. Okay, part B asks us approximately when did the population reach 50,000? So in this case, it wants to know when P of T was equal to 50,000. So we're solving for T now. Okay, so we want to know what T is equal to. Everything else stays the same. So we set this up as 50,000 is equal to 6,250 times 1 plus 0.0275 raised to the T. Now, one thing to note is your calculator is not just going to solve for T for you. Okay, this is where what you were talking about, like making the L earlier, is going to come back into play. So first of all, 50,000 divided by 6,250. Pretty sure that comes out to be even. Can one of y'all divide that? Huh? 8. So 8 is equal to 1, and I'm just going to go ahead and put 1.0275. Okay, I'm going to go ahead and just add that together and raise that to the T. Now remember, when we are doing an exponential to a log, we need to put this 8 on this side to make the L. Okay, so I'm going to move that over. So to make the L, we come down and across and back over. So we've got log base 1.0275 of 8 is equal to T. And then you can do this in case you need a refresher on your calculator to get log base, hit the math button. Oops. And it's alpha A under math. And that gives you log base, and it gives you a little box to type the base in. And then it'll give you some number for the number of years. So how many years was it? 26.65 years. And a lot of times these questions want to know, when it says when did the population reach, it doesn't necessarily want to know how many years from the initial, it wants to know the actual year. So in this case, we just need to add basically 76 years to the initial, 1890? So 1890 plus 76 gives us what? What year? 1966. So it happened in the year 1966. This is how many years it took for the population to be 50,000. All right, so we've got right about 10 minutes left, and I just don't feel like that's enough time to really do another one. Not that it necessarily takes that long, but just with explaining everything. We'll hold off on the next one. So what I will tell you, okay, obviously, problems I would have assigned here would have been 1 through 11 odd, and I would, let me see, let's try 21. I really would like you guys to do 21. The other ones, okay, it's up to you. Like I said, I'm not going to be super strict about you guys doing all the homework. I will, you know, it's more like do what you feel like you need to do to understand the material. But 21 is a word problem that would be a fair game for like a quiz or test. 22, since we did it, would be fair game. And then tomorrow we'll talk more about other options of problems with this other worksheet that I think just explains stuff really well. So.